All right, the promise, I don't want to start every video with all right, but I did. The promise was the first video would be the worst, and then it's going to get happier and happier and happier from there. Well, this video should be hopefully happier. All right. And should be a little shorter. We got some properties, and these properties should look really familiar. If they're not, don't worry. I won't take off points. But let's jump into them. Property. Well, all right, some of these properties look familiar. The first one probably won't look familiar. All right, we got a bunch of properties. Let's make room for all 5 on this page. The integral from a to a of any function with respect to x. I spoiled it. I shouldn't have spoiled it. It's 0. Why is that? Because the definite integral is area. So if I'm looking at a curve, and I'm saying, what's the area between 1 and 1? What's the area of this vertical line? Well, a vertical line is a one-dimensional thing. It has no area. The width is 0. There's no area here. It's infinitely tiny. That's what this first property is all about. We won't see that one too much, but we'll see it from time to time. The second one is also kind of weird. When I said they'll look familiar, I wasn't talking about the first 2. 3 through 5 should look familiar. The second one says the integral from a to b of a function is the negative integral from b to a of the function. In other words, if we switch the limits of integration, instead of going from left to right, if we go right to left, that's just the opposite. That one's a little kind of weird to see. It'll really come into play later on in this chapter. So this one's kind of a little foreshadowing, okay? Obi-Wan's staring off into space saying, I knew your father or something. Something about the Clone Wars. I don't remember my Star Wars lore. This one won't come into play too much until later in this chapter, but when it does, you'll see why. Number 3, and also the rationale for this is kind of like the same rationale as negative exponents, where it's kind of defined to be this way because it's consistent with other rules that we think about. But I'm getting ahead of myself. That's not in 1.2. For now, just take it on faith. If I have 2 functions and I'm adding or subtracting them, what do you think this integral is going to be? Well, the integral is just the area. We're adding 2 functions together. Their areas should add up together too. And these areas are just Riemann sums, and we had a property for this exact thing in the last section. Yeah, it's just going to be the integral of the first plus the integral of the second, which is really, really handy for when we get to some integration shortcuts. Oh, and it's plus or minus. It works for addition and subtraction here. All right, the next one should also look familiar. The integral of some constant times a function. What do you think we can do with that constant? I'm going to leave it blank for a second. Number 5. The integral from a to b of some function can be split up. It's the integral from a to c of that function plus the integral from c to b of that function. We had something very, very similar to number 5 for summation notation, for sigma notation, right? And we're summing up n things. Well, that's just the first m plus the rest. This is exactly what's going on here. And c doesn't even have to be between a and b, by the way. C can be outside of that interval, and it still works because of this guy. All right, hopefully you can pause the video and fill in number 4. But if you want spoilers, I'll spoil it. Just like the summation thing, we can factor out a constant. Just like derivatives, we can factor out a constant. Most things, that's not true. A lot of things in math are linear which means that we can factor out constants. I'm not going to get into the definition of what a linear operator is. We know what linear functions are. Linear operators are more confusing. But yeah, this we can factor out a constant. Absolute values, we can factor out absolute values of constants. Trig functions, nope. Cannot factor out a constant out of those guys. But most things with addition, we can factor things out of. And this really is just addition, just adding up an infinite number of infinitely tiny things. That's calculus 2 in a nutshell. Adding up an infinite number of infinitely tiny things. Really just in general, calculus is really just all of calculus is really just talking about infinity. Derivatives were infinitely tiny secant lines. Integrals are just infinitely tiny rectangles. Calc 3, we talk about sequences and series of infinitely many things. And Calc 4 is like vector calculus. I think here it's different in different places. Anyway, I'm really going off topic. Believe it or not, I like talking about math. But we don't want this video to be an hour long, so I'm going to stop myself from talking about math, and we're going to get on to example 5. Assume that the integral from 0 to 8 of some function with respect to x is 10, and the integral from 0 to 5 of that same function is equal to 5. I'm not telling you what this function is, but I'm saying the area between 0 and 8, assuming the function's positive, is 10. Okay. And if the function's not always positive, then I'm telling you that the net signed area is 10. So let's calculate some stuff. And again, this is a really good opportunity for you to pause the video and try to do this on your own using those properties. But if not, we can do them together. Find the integral from 5 to 8 of this function. And again, it might be helpful to think about this graphically. All right, we're looking at the interval from 0 to 8, and there's something happening at 5. Who knows what this function looks like? But I know that this total area is 10. This is not going to work, but I'm going to try it. And I know the interval, this area from 0 to 5 is 5. The question becomes, what's the area from 5 to 8? Which is 3. If you know your properties, and you know what areas is, well, if the total thing is 8, this portion's 5, what's left over? Yeah, just 3. So we can write this out with the property. All right, that's going to be the total area minus first part. And that's just 10. Wait, it's not 8. It's not 8, guys. It's 10. I made such a big point about how easy this is, and then I got it wrong. It's 10. All right. So 10 minus 5 is 5. Great. Let's move on before I feel dumb. That's another downside to recording videos instead of doing it in class. You do it in class, people usually let you know a little sooner. Here, I got to figure it out. 2 times a function plus 5. Now, this one's trickier. This one's going to have to require a couple steps, a couple, I almost said something weird. A couple of steps more in depth. You're going to have to use your noggin. So let's use the properties. Properties say that we can add things together. I don't have to worry about changing the limits of integration. We already have information from 0 to 5, so the limits of integration are good. Let's just split this up into a bunch of pieces. All right, so using the sum law, this will be the first part, integral, plus the second part, integral. Now, we still have to do a little bit with each of these parts. The first part's not too bad, right? 2 is a constant. We can factor it out. And get that this area is 2 times the integral, which we said was 5 up here. The second piece has nothing to do with f at all. You might say, well, Jason, it doesn't have anything to do with f, so we don't know. But we do. Think of this as some other function. If that's some function g, and g is just the constant function 5, well, what's the integral from 0 to 5 of this constant function? Was 25. Okay. Definite integral is just area, as long as everything's positive. So we should get 35 as our answer here. Part C. Integral from 8 to 0 of our function. Okay, we have a problem with our limits of integration. Well, not necessarily a problem, but remember how I started this one by saying our limits of integration are fine because they match information that we know about the problem. But that's no longer the case, right? We know the integral from 0 to 8, but we don't know the integral from 8 to 0. That's where we use that second property. This is the opposite of, whoa, that's not an 8. That looks like an infinity. It's just the opposite of if you switch the limits of integration. So it's going to be -10. And again, this kind of deal, we're really not going to come up until later on in this chapter. Last example of the video. Integral from 4 to 4 of this function. We're looking for the area, this vertical line, from 4 to 4. How much area is there? Nothing. No area. That's our first property that we wrote down at the start of this video. Got a big donut hole. It's like the donuts I was doing in my Nissan Versa Note. All right, that's everything for this one. There's some tricky problems in here, but there's some more. I do some extra problems at the selected homework problems video. So hopefully you can apply these and get cracking. Good luck. Bye-bye.